I'm representing this year's committee for the SIGecom Doctoral Dissertation Award. This was composed of Nicole Morlika, Aaron Roth, and myself. And on behalf of the committee, I'm very happy to introduce to you the winner of this award, Peng Shi. We had a number of excellent nominations this year, and Peng's thesis stood out in terms of, in addition to its very impressive theoretical contributions and novel directions it introduced to market design, it's had an unusual level of practical impact. The school assignment proposal procedure that Peng proposed has been implemented and adopted right here in the city of Boston, and this was even before the thesis was completed. In the words of one of his endorsers, Peng's thesis is exemplary in completing the arc from theory to practice and serves as a role model for all of us. So congratulations.
Thanks so much for the introduction. It's really my honor and pleasure today to present my thesis. I graduated last year at MIT with a PhD in operations research, and my advisor is Itai Ashlagi. So the motivating application of this thesis is school choice, which is about how to assign students to public schools in a way that takes into account their preferences. So it's an important problem because every parent wants their child to go to the best school for them. But it's a difficult problem because resources like capacities at schools or city school busing are limited. So it's hard to satisfy everyone. You have to make hard trade-offs. So there are two components to this thesis. One is prediction, and the second is optimization. Now, prediction is about, given a school choice system, predicting how will families behave under this system. And optimization is about, given a predicted behavior, how to find the best system. So I started getting into this problem in 2012 when I saw this news article that the Mayor Menino of Boston wanted to reform the student assignment system. And he put together a city committee, and I attended many of these meetings which were open to the public, talked to parents, school board staff, policymakers, and learned about what are their concerns. And it's been a very fruitful time. I'm very thankful eventually to have the opportunity to analyze data, work with Boston Public Schools, which also led to several theoretical research projects. And so let me first discuss the problem by covering some background on school choice, as well as how this research question I will define is related to the literature. And then the main body will be the prediction and the optimization. So here's how school choice works in many cities in the US. So based on student characteristics, such as where you live, where your siblings are, etc., each student receives a menu of options, which is a set of schools. And students out of this set can submit a preference ranking, which means what is my first choice, second choice, third choice, and so on. In Boston, students can rank as many schools as they want. On the other hand, schools also assign priorities to students. You can think of this as each school giving each student a number, and whoever has a higher number wins at a particular school. So given these two inputs, the preference rankings of students and the priorities of schools for students, an assignment algorithm outputs a school assignment. And in Boston, the first round of assignment, which covers 80% of students, happens in January or February, the year before school starts in September. So here's how let me talk to you in the next two slides about the reform in Boston. So in 2012, this is the school assignment system in Boston. Here's a map of Boston. It's divided into 3 geographic zones: the North Zone, the West Zone, and the East Zone. This reform is focused on elementary school assignment, which means kindergarten 2 kids, so 5-year-olds. There's about 75 schools, so about 25 schools in each zone. So the choice menu is any school within the zone that you live, plus a 1-mile radius around your home, which is called your walk zone. And for the purpose of this talk, priorities are, first, priorities are given to those people who live within the 1 mile, and then it's random numbers to break ties. But to give people outside of the 1 mile a chance, this priority only applied to half of the seats. And the assignment algorithm is the Gale-Shapley deferred acceptance algorithm we teach in matching. Essentially, first, students apply to their top choices. School will fill seats as available. And otherwise, if there's not enough seats, then they start bumping out the students with the worst priority. And then those students then apply to their subsequent choices until every student is either assigned or has gone through their entire list. So this algorithm has many desirable properties. But let me talk a little bit about this whole system as a whole, why they needed a reform. So here are some benefits of this system in 2012. The first one is that choice is good for families because they may have information on what their child needs. Second, it helps the school board do capacity planning because instead of each school needs to cover its own region exactly, there's a capacity pooling across the zone. Thirdly, this is perhaps more equitable than simply assigning everyone to their closest school, especially if your closest school is not very good. And lastly, this Gale-Shapley deferred acceptance is incentive compatible for students to submit their true rankings. However, there are also some issues with this current system in 2012. The first one is the high transportation cost. So in 2012, Boston spent $90 million a year, which is 10% of the entire school board budget on busing kids around. On a per capita basis, this is 3 times the US average and almost twice that of New York City. Secondly, community dispersion occurs, which means that neighbors on the same street may go to different schools because they get different lottery numbers. And as a result, parents may not know their neighbors because a lot of parents say that they socialize based on who their kids play with. And this is a cost to the city. And thirdly, these choice menus are not centered around the student because if I live near a boundary, there may be many desirable schools most of my options will be on one side, but there may be a school just outside of the 1 mile that's I cannot choose from. Also, it's unpredictable because there's no guarantee I will get my top choices. And there are also inequities across the different zones. School qualities are different. So as a result of these reasons, Boston wanted to launch a reform. And so I went and talked to these parents, and one thing they said is that anything that can be implemented needs to be explainable to a 5th grader. So a constraint is simplicity. So I came up with some simple proposal, and it's as follows. Instead of the 3 zones, we construct the menus based on the union of several sets. So every student will be able to pick in their set of schools any school within the 1 mile radius, the 2 closest tier 1 schools. So as background, Boston Public Schools classify schools based on their test performance into tiers, and tier 1 is the best. So 4 closest tier 1 or 2 schools, the 6 closest tier 1, 2, or 3 schools, and the 3 closest big schools. So the reasoning is as follows. So reducing the set of schools reduces the busing cost. Also, by definition, all these schools will be centered around the student rather than based on some boundary. And most importantly, if my closest 6 tier 1, 2, or 3 schools already include some tier 1 schools, then I don't get extra schools from this union because I already live near the good schools. But if my closest 6 tier 1, 2, or 3 schools are all tier 3 schools, then I do get extra schools from this union. So it compensates students who don't live near the best performing schools with more options. But this is a heuristic, and the question is, how will we perform? So the question of this thesis is essentially how to optimize the menu and the priorities given the deferred acceptance algorithm in order to achieve good outcome, as seen by saving transportation money, making students happy with their choices, making it predictable, also helping neighbors to go to school, the same school with higher probability. So let me discuss how this research agenda is related to different lines of research. There's one line of research in operations research which doesn't have choice. It's just the optimal assignment of neighborhoods to schools to accomplish some objective. There's a rich literature in economics on matching that focuses on the assignment algorithm. In particular, this literature mostly treats the preference rankings and priorities as fixed inputs. But here, we're optimizing over these things. So we're building this optimization model on top of deferred acceptance. This is also related to some recent previous work by Tim and many others here in this mechanism design without money literature, which is in abstract, how can we design some incentive-compatible mechanism to accomplish an objective? And the difference with this thesis is that we have this specific structure that filters through deferred acceptance from institutional constraints. So that's the relationship. So now I'll describe how the prediction and optimization are related to one another. So in order to optimize the choice plan, we need to predict what will happen under any menu and priorities. That involves forecasting the population, who will apply, predicting choices under new set of options, which we haven't seen before in the data, and also simulating the outcome. And the hardest part is this, which is what I will focus on. So now I will go into the prediction part of the thesis. So here, the main contribution is not methodological. Rather, the techniques are already present, but it's more empirical, and we will see we do some field validation of various models. So how do we model preferences? The end goal we want to do is to compare some choice menus. So here is a map of Boston. Each dot is a small neighborhood track. And then here's a home location. And this is the set of schools this family has under the previous 3-zone plan in 2012. And this is the set of schools under the home-based plan. So as we see, although the set is reduced, there are some new schools under the home-based plan that's not present under the previous plan. So, and one way to compare how happy are people under these two plans is this metric, which is we built some utility model for students' I's preference for school J, and judge a set of schools by the expected utility you will get. And so more precisely, the data we have are the students' school characteristics from the past under the 3-zone plan. And also, as well, their choices, first choice, second choice, third choice, and so on. So we want to estimate this multinomial logit model in which the utility of student I for school J is equal to this quality of school J that we estimate from data, minus the distance, plus a linear function of student school characteristics, like whether the student has a sibling at a school or the student's race interacted with the school's demographics, plus an unobservable error term that we model for convenience with the Gumbel distribution. So one can estimate this using maximum likelihood from the ranking data, and the things you estimate are the qualities, the gamma, and the beta. So this model is normalized with respect to distance. As you see, the distance has no coefficient. And the logic is this. We want to estimate from ordinal data how much do people like something over another. And the idea is, suppose there's two schools and we're at a neighborhood equidistant to them, and maybe more students prefer school A over school B. Now consider the thought experiment of moving toward school B. We'll find that more people are substituting to school B because of the distance. And measuring this rate of substitution helps us to get a scale at how much do people generally like one school or another. So this is one simple utility model. There are other ways you can do. You can do a simple hierarchical model that doesn't use utilities based on some rule that you think makes sense. As well, maybe use a mixed version of this MNL model in which the coefficients may follow maybe specific for each student and follow some random distribution, so more complex models. For this talk, I'll focus on this one, but a lot of the prediction part of the thesis is comparing between the performance of these, and we do find that this one has near optimal performance and is much simpler than this more complicated model. So based on this utility model, we can now evaluate the outcomes of interests. So for busing cost, we can simulate simply how far students have to travel, as well as what area schools need to cover to pick up children. For students' happiness, we can simply simulate these utilities for each neighborhood track and take either the average or the minimum. As well, we can study predictability and community cohesion, defined as how many neighbors are going to the same school as you. So just to test the prediction methodology, we see that the home-based plan gives people fewer choices, which result in a large reduction in the busing. However, students' happiness, as predicted by your utility model, also decreases, with no change in predictability, and students are going to school with their neighbors. So based on this kind of comparisons, Boston in 2013 decided to adopt the home-based plan, and this was ratified by the school committee, and here's me in the background. Yes, so after this reform, and this has been implemented in January of 2014, so this is already 2 years, and there's many other changes that came afterwards that's unrelated to me, and I guess the main result right now of this is that it shifted the debate about school assignment to the more important problem of school quality, which is what's underlying a lot of these school reforms. I can discuss more about the practical side later. So after this reform also allow us to do this empirical test of these various models. So part of the thesis is before this reform, we use different models to predict what will happen. And then after the reform, we compare the prediction. So it's a truly out-of-sample test of these models. And we find that the MNL model doesn't perform perfectly, but it's reasonable. So for the remaining of the talk, I will assume the MNL model and think about how to really optimize these menus and priorities. I'll formulate the problem as well as talk about two techniques that makes the optimization tractable. One is this large market approximation, and which relates the problem to this literature on assortment planning, and also how to find algorithms to compute these assortments. So the optimization problem can be formulated as follows. The decision variables are the menus and priorities, and we want to maximize a weighted sum of how happy people are on average, as well as making sure no neighborhood is very badly off, while staying within the constraints of the home-based plan with respect to bus coverage and busing. So the idea is take whatever resources used in the home-based plan and optimize it. It's a very difficult problem because priorities couple things together, and there's just too many things to try by brute force. So this is a very multi-dimensional kind of mechanism design problem if you want to solve the discrete version. So the approach is as follows. Instead of solving this problem on the left, where we optimize menus and priorities subject to this MNL model, we consider this other problem, which is a theoretical construct used only to find a solution, but we'll actually be implementing this one. And in this other problem, it's as follows. So based on each home location, we find a random assortment, which is a set of schools, a random set of schools. With each student simply pick their favorite school in this set, and that's their assignment. So this avoids all these deferred acceptance complexities. And the idea is to find the optimal assortments and use that to construct the menus and priorities. And the reason we can do this is as follows. In this large market model in which we take the number of schools as fixed, and scale up the number of students along with the capacity of schools. In that limit, it turned out that these two models are equivalent in the sense that we can construct mappings that we can write down that maps menu priorities to assortments and vice versa, such that the objectives will be the same. And this equivalence kicks in even only when the school sizes are like log square the number of students. So you don't need really, really large schools for this to kick in. So based on this, we just want to find the optimal assortments and use the mapping in the proof of the previous result to construct, to do the second part. And when doing this, we can apply a common technique of column generation to reduce this problem to a simpler problem of, for a given individual neighborhood, find a deterministic assortment of schools such that when people pick according to the MNL model, there's a good objective according to this, which is a weighted combination of how happy people are with this set of schools, plus the externality they impose on others. So by externality, we mean, for example, assigning every student from this neighborhood to this school incur an externality of 4 because we're using either capacity or busing resources. These are opportunity costs. And for example, the optimal set might be this. So one thing to note is that when alpha is 0, we only care about the externality term. And that's the same as this revenue maximizing assortment problem, which is studied in operations. In that problem, it's like a supermarket optimizing what set of options to put on my shelves so that when people come, I make a lot of money. But here, we're optimizing, a school board is optimizing what set of schools to show to a neighborhood so that to make that neighborhood happy while accounting for the opportunity cost on other people. So mathematically, it looks something like this under the MNL model. We're trying to find a set of limited cardinality to maximize this log term plus this ratio term. And the cardinality constraint is a heuristic to make sure that the busing area for each school is limited. And the question is, can we find a polynomial time algorithm for this? When S needs to be basically up to 100 and K is, can we find an efficient algorithm? So the one thing is that we can leverage now this operations literature on the revenue maximizing problem. And what we see is that, in fact, you can tweak the proofs to make them work also for the socially optimizing case. And the proof is based on reducing both problems to a more fundamental problem and solving that using techniques from the literature. And we can do this kind of transformation not only for the MNL model, but also other discrete choice models, also other kind of constraints. And finally, the output we have is, as before, a menu for each neighborhood, a set of schools, as well as priorities that take this intuitive structure. The priority of student I for school S is equal to some neighborhood-specific constant plus this IID lottery number. So we can implement this within the current framework that they already have. And this is what the results are from discrete simulation. So these are the tables from before. What we see is that the optimized plan matches the busing savings of home-based by construction, makes the average student more happier, as well as make sure that this utility improvement is across the board. The whole distribution moves up. It's more predictable now. You have a 96% chance of getting your top 3 choices. As well, community cohesion is improved. So we see that this optimization plan gets the best of both worlds. And one thing, nice things to note is, even though we didn't explicitly optimize for predictability, we got this for free because when you solve a linear program, the solution tends to be sparse, and that's what's driving this. So that concludes my presentation. To summarize, we modeled this real-world reform, did some empirical validation of this commonly used model, as well as found ways to optimize the inputs to deferred acceptance based on 2 theoretical contributions. One is connecting matching with assortment planning, and the second is algorithms to solve for these assortments.